So the last Thursday of term, it's a great pleasure to introduce you to somebody who nobody knows. Of course not. So, but I'll introduce James Dunderstone. Thank you. Much like the introduction I gave James is well known to all of us, of course. He read physics and philosophy here as an undergraduate. Again, he went to the other place, but only for a year. So we'll let him away for that. Returned to do the DPhil. Yeah, then almost went to the other place again for a bit, but then was rescued. And has been a marvellous mainstay of Oxford philosophy of physics for some considerable time, always coming up with lots of exciting new mathematical, physical, philosophical things. So today we're going to be delighted with a new trinity. Over to you, James.
Thank you very much, Chris. So what I'm going to present today is based on joint work with graduate student superstars Will Wolf and Eleanor March, both in the room today, and also with Quentin Vigneron, who might not be known to you, but he's a talented French mathematical physicist now based in Poland. So this is joint work with all three of these people. Before I get onto what exactly I'm going to talk about, I just want to make some hopefully uncontroversial remarks about the state of the philosophy of space-time canon in modern times. So, recent philosophy of space-time canon surely includes the following, amongst other things. Geometrization and recovery. So, it's pretty well known by now that if you start off with flat space-time Newtonian gravity with a gravitational potential, you can combine the flat space-time derivative operator and the gravitational potential into some curved derivative operator, or what ends up being the theory known as Newton-Cartan theory, which is in some sense the non-relativistic version of general relativity. So philosophers of physics know this quite well by now. These results go back to Troutman in the 60s, but Jim Weatherall's written a lot of papers about this, and if we were to go to our go-to source would almost certainly be Malaman's book here. Okay, the next thing is non-relativistic limits. So again, lots of different philosophical discussion of this over the years. We have papers from Malamant in the 80s about widening light cones. We have nice discussions about the non-relativistic limit in Harvey's book, for example, and in lots of other places besides. A nice recent paper on this is Sam Fletcher's paper about the non-relativistic limit of relativistic spacetime. So that's one that I would recommend to you as well.
Speaking of whom?
You just missed your name drop.
I'll have the pleasure of it later.
just say it again, James.
The third element of the philosophy of space-time canon, Maxwell gravity. So it's becoming increasingly well-known and familiar and mainstream, this topic. The idea in recent times goes back, I think, to Simon's paper, this idea that you might be able to formulate Newtonian physics, not in Galilean space-time, but in some weaker space-time structure, which has only, say, a standard of rotation and not a standard of non-rotational acceleration. Worth flagging that Simon was actually lecturing on this way before 2013. So I was chatting to him on email yesterday, and he said at least since the mid-2000s he was talking about this topic. So again, this has been around for a while and relatively well-known. Just to mention other people who have worked on this, so we've got people like Jim Weatherall and David Wallace and Eleanor Knox and Nick Tay and Neil Dewar and Eleanor March and others. Cool. And maybe not quite so much, but increasingly geometric alternatives to general relativity. So Eleanor Knox's 2011 paper about teleparallel gravity, about which much more later, but in brief, it's a theory in which gravitational effects are a manifestation of space-time torsion, not space-time curvature. This is pretty well known now. It's got hundreds of citations. And more generally, and I'll talk about this much more, the geometric trinity of gravity, this kind of trinity of different theories of which general relativity is but one node, but in which gravitational effects are manifestations of different kind of geometrical features, is becoming increasingly well known to people. Maybe not quite so much as the other ones, but we're getting there. Cool. And there have, of course, been some discussions about the relationships between these things, maybe most notably between Maxwell gravity and geometrization / recovery. So people ask, like, how is Newton-Cartan spacetime related to Maxwellian spacetime? I'll avoid, like, citation dropping. But you all know who to read, right? But there's more to be done. I think there's much more to say about how these four topics relate to each other. And that's going to be the goal today, to say a bit more about how these interlink and to hopefully reveal interesting questions for future philosophical pursuit by doing that. Okie doke. So there are kind of two main goals for today. So the first thing that we're going to do is we're going to take the relativistic geometric trinity and we're going to take its non-relativistic limit and we're going to construct a novel non-relativistic geometric trinity. So that's already combining these two things. By constructing that non-relativistic geometric trinity, we're going to be able to contextualize maybe a little bit better where geometrization and recovery fits in. So I'm going to connect the non-relativistic trinity with that first question as well. And then we're also going to ask kind of what's the invariant dynamical structure of the non-relativistic trinity, and there Maxwell gravity is going to come in. So we're going to see all of these things kind of coming together. Good. Just to repeat, this is joint work with Eleanor and with Quentin and with Will. It's based on two papers. The first of these is with Will and Quentin, and that's about constructing the non-relativistic trinity. And then the second is with Will and Eleanor, and that's about looking at the kind of like common mathematical structure of the nodes of the trinity. Good. So the plan for the talk is this. There's nothing original in the first part. I'm just going to remind you about the relevant aspects of differential geometry and what the geometric trinity is, remind you about what geometrization and recovery are, and talk a little bit about the classical limit just to get the pieces on the table. Then in the second part of the talk, we're going to construct the relativistic trinity. This part is going to be based on the paper with Will and Quentin. So we're going to write it down and then we're going to explore some various aspects of it. Then in the third part, which is based on the paper with Will and Eleanor, we're going to look at the common structures of the relativistic trinity and the non-relativistic trinity and see what's going on there. And then I'll close by gesturing at stuff which we haven't done yet, but want wish to do. Hopefully that sounds okay to everyone. Good. Okay, so let's kick off then. So differential geometry basics. So don't worry about this too much, but like predictably there are going to be a whole bunch of different connections floating around in this talk. And let me just list them to you, but you don't really need to remember what's a hat and what's a tilde and so on. Tell you that there's different things going on. So we're going to be using first Lorentzian-Levi-Civita connection with associated covariant derivative operator, which is the metric, and with associated Riemann tensor. But we might also be interested in more general relativistic connections, which have other geometric properties like torsion and non-metricity, which I'll go into in a minute. And I'll denote those more general guys with bars over the top. In the non-relativistic side, we might be interested in a non-relativistic derivative operator, which is compatible with our two metrics. By the way, I will explain this more in detail in a minute. And which doesn't have torsion or non-metricity, and I'll denote those guys with hats. But we might also be interested in a more general non-relativistic connection, which perhaps does have torsion and non-metricity, insofar as a connection can have non-metricity. I'll come back to that in a second. And I'll denote that with tildes. So there's a whole bunch of stuff going around, but don't be making notes about what's a hat and what's a tilde. I'm sure it will be. I hope it will be clear. Okay. So there are three geometrical properties that we need to understand in order to understand the geometric trinity of gravity, and I've already mentioned them. But just to remind you, these three things are going to be curvature and torsion and non-metricity. And curvature is by far the most familiar to us, I'm sure. And curvature measures the extent to which if I take a vector and I transport it along a closed loop, the extent to which the vector comes back pointing in the same direction or wrong. The rotation of a vector transported along a curve is given by the curvature. By the way, this image is stolen from a survey paper about the geometric trinity by Lavinia, Heisenberg, and collaborators. Those are the main that's the biggest group of physicists who work on this material. So that's curvature, but we also have torsion. Roughly speaking, heuristically speaking, this measures the extent to which going one direction and then another doesn't commute with going in the other direction and then the first one, but maybe better put as the non-closure of parallelograms formed when two vectors are transported along each other. So the extent to which these parallelograms don't close is given by the torsion tensor T. And finally, we have non-metricity, and this measures the extent to which the length of a vector changes as it's transported along the path. So these are three different geometric properties associated with these different mathematical objects. If I wanted to write these things down, or the curvature tensor or the torsion tensor or the non-metricity tensor in terms of connection coefficients, well, we're very familiar with the expression for the Riemann tensor. You will have come across that in a first course on general relativity. The torsion tensor measures the antisymmetry of the connection. So you just anti-symmetrize the lower two indices of the connection to get the torsion tensor. The non-metricity tensor just quantifies the extent to which the covariant derivative doesn't kill the metric. Just as a kind of side philosophical point, you can clearly see from the way that these are written that these are kind of like torsion and curvature are kind of intrinsic properties of a connection, whereas I think non-metricity better understood as a relational property between a connection and a metric. Another thing that anyone that's done a first course on GR will have encountered is the expression for the Levi-Civita connection coefficients in terms of the metric and its derivative. So that's just this expression. And if I wanted to write down the coefficients of a more general connection, perhaps with torsion and non-metricity, it would look like this, where I have a difference tensor between my Levi-Civita connection and my generic connection, which is built out of the torsion tensor, and this is called K, and this guy is known as the contorsion tensor. And I also have a difference tensor between my Levi-Civita connection and a generic connection with non-metricity, and that difference tensor is denoted L, and that's known as the distortion tensor, and that's defined like this. So I've got torsion and non-metricity, and associated respectively with torsion and non-metricity are contortion and distortion, which are the differences between the connection coefficients for my original Levi-Civita connection and the new thing with torsional non-metricity. So yeah, I could just take the difference between the Levi-Civita connection and this generic thing, and this would be the difference tensor. This is just really writing out the same thing again. So I've got my kind of distortion part here in terms of the non-metricity, and then my contortion part here in terms of the torsion. Everyone happy? Okay, that's the first thing done. So now we can talk about the geometric trinity. So what we're going to use is everyone's favorite expression, Malament proposition 1.8.2, including the torsion tensor. So you've got to remember that Malament very early on in the book says, I'm only interested in torsion-free connections, which is completely fine. But that means that in Malament, this term doesn't appear. But if you actually want to write down the difference between the Riemann tensor of one connection and some other connection with torsion as well, potentially, it would be this expression. And then if I'm interested in the difference tensor between one connection and some other thing with torsion, then this would just be the the contortion tensor here for M. And if it were between the Levi-Civita connection and some other connection with non-metricity, it would be the distortion tensor here. Generically, so this is going to be the difference tensor between this is going to be expression relating some original Riemann tensor to some new Riemann tensor for some other derivative operator associated with torsion and non-metricity as well. Cool. That formula plays a key role in articulating the geometric trinity of gravity. Because what you do is you just take, say, the Einstein equations, or you take, say, the Einstein-Hilbert action, and you replace the Ricci tensor or the Riemann tensor or the Einstein tensor or whatever it is that you're looking at with the kind of equivalent expression for some other connection which might have torsion but no curvature, say. So if I'm thinking about things in terms of Lagrangians, is the Einstein-Hilbert Lagrangian? If I use that formula on the previous slide to swap out the curvature there for some torsion for some other connection which is flat but torsionful, I would get the second thing up to a total divergence term. And if I do the same thing but I swap out the curvature for non-metricity, I would get this thing. And I couldn't be bothered inserting all of the Q's here, so I just kept it in terms of L's. But ultimately, this is also a function of non-metricity, right? Just like this is a function. This is just torsion. These guys differ, as I say, by total divergences. So the actions differ by a boundary term. And that's kind of crucial in people arguing that these are going to be dynamically equivalent theories, because if the actions differ just by a boundary term, then that's not going to affect. There's going to be a sense in which you get equivalent equations of motion for these theories, even though you've got one theory written in terms of torsion and another theory written in terms of non-metricity and another theory written in terms of curvature. Will and I have had various backs and forths with various people about whether it's right to say that this is dynamical equivalence, but this is what all the physicists say, and it seems okay to us, but we can come back to it and discuss more if you like.
Sorry, is it right that with the vacuum
Here, yes, but you can do the same flipping around with the material sector. And actually, I'm just about to show you how this works at the equations of motion level, and you can actually include like matter as well. So I'll show you. Okay, so in terms of equations of motion, you have this lovely slide. So I use the trace reversed Einstein equations because it's easier to just swap out the left-hand side if I've just got one object, one like geometrical quantity on the left-hand side. So I have the stress energy tensor or its contractions over here. So what I do is I just replace that Ricci tensor with like the equivalent expression in terms of torsion for the teleparallel theory, the torsionful but flat space-time theory associated with general relativity. Or I do the same thing by replacing that with the associated expression for non-metricity for the what's known as the metric teleparallel theory, the theory with no torsion and no curvature but non-metricity. So we're using this kind of geometrical trick, as it were, to move between three space-time theories. One which has curvature but no torsion and no non-metricity, that's just good old general relativity. One which has torsion, no curvature, and no non-metricity, that's what we call the teleparallel equivalent to general relativity, TEGR. And one with no curvature and no torsion, but non-metricity, and that's known as the symmetric teleparallel equivalent to general relativity. Another image stolen from the Heisenberg et al. Paper, maybe this may or may not be illuminating, but basically got a trinity of theories, and they have roughly similar actions if you just define all of those like long expressions for torsion or curvature, which I showed you before is conveniently the torsion scalar or the non-metricity scalar, and they all kind of look structurally the same. But this theory, general relativity, has curvature, no torsion, non-metricity. The teleparallel equivalent has torsion, but neither of the other two, and the symmetric theory has non-metricity, but neither of the other two. Enrique?
Very quickly, each one of these has an action, and when you get the equations of motion in the Einstein action, you're varying for the metric. These other ones, what are you varying for?
You still have a there are lots of different ways in which you can formulate the theory, but you have a metric and you have a derivative operator. So these people often proceed with a Palatini style approach with both of them, vary with respect to both of them. It's going to be a different derivative operator in the theories, but the same metric.
You vary with respect to both the connection and the metric.
A second, but we can carry on talking about it later. Cool. Does anyone else want to say anything? Cool. Good. Okay, so you might think that this is a mere shell game because I'm just shuffling geometric degrees of freedom around. But I would resist this on two fronts. Like, first of all, absent any further philosophical discussion at this point, a super naive scientific realist might say these are distinct theories. One of them paints the world as consisting of a space-time with curvature, and another one describes the world in a apparently distinct space-time with torsion, etc. And those seem like distinct things. Maybe you think that's a bad argument eventually, but it requires at least some philosophical work to articulate why that's a bad argument. Even setting that aside, physicists actually do like all three nodes of this trinity and think that it's worth studying them. And here are a few different reasons why they do. First of all, they have different gauge structure in interesting ways. So the teleparallel theory and slightly more confusingly also the symmetric teleparallel theory are sometimes described as gauge theories of translations. Cosmology, so they have different applications in modeling the early or late time evolution of the universe. They have different virtues with respect to modeling boundaries like black hole boundaries. It actually turns out to be easier to use teleparallel gravity in this respect than in general relativity. They offer different routes to quantization, perhaps because you're sticking like a different action into a path integral. And they have different opportunities for generalization. So people would pursue these for a whole bunch of physical reasons as well. Yeah.
Are these sort of mostly like differences in ease of use as applied to different things, or things that people think will actually lead to finding that the different theories have different predictions?
They don't. I think almost everyone has agreed that they don't have different predictions. It's like an ease of use thing. But the generalizations, there's not so obviously a trinity for like the f of this kind of f of generic function of R, function of T, function of Q case. People have started trying to find like trinities for more complicated generalizations of these things. It's not well understood yet. Okay, so geometrization and recovery. this is a bit more familiar to philosophers. So here's a classical space-time. It's got 4 things in it. It's got a manifold, a clock form, spatial metric, and degenerate spatial metric, and a derivative operator. And T or tau and H are compatible in the sense that they're orthogonal. And we're going to start off using what we call a Galilean connection, which is one which is compatible with both tau and H. Unlike the Levi-Civita case, there are some ambiguities in a Galilean connection. So it's not like nabla G is equal to 0, which kind of already tells me what the form of the connection coefficients are. Just having nabla T is equal to nabla H is equal to 0 doesn't actually like uniquely fix the form of the connection coefficients. And there's some ambiguity. Ambiguity in particular in the choice of time-like vector field, which appears in that expression, and also in choice of 2 form, which is called the Newton-Coriolis 2 form. So the connection coefficients for a Galilean connection look like this, where I've got some kind of Levi-Civita-ish type thing, but with the downstairs, the inverse of H, which we call B, which is in fact not unique because H is degenerate. So it's actually only fixed up to this like factor with this vector field big B here. And then also over here, so I've got a term featuring that big B as well, but I've also got this Newton-Coriolis 2 form term over here, and that will take this, it could be expressed in this way using the little b and that big B. So you have to make some more, you have to fix some more stuff to fix a Galilean connection uniquely, unlike in the relativistic case. You look unhappy, Eleanor, are you? Okay. Stressing me out. So far this doesn't include torsion or non-metricity. This is just an ambiguity or the fact that this connection isn't fixed, even assuming no torsion and no non-metricity. Okay, so using such a connection, I could build Newton-Cartan theory. This is my curved space-time version of non-relativistic gravity. And it has the following equations. It's got the geometrized Poisson equation here. It's got the first homogeneous Troutman condition here. I'll explain what this does in a second. And you have covariant conservation of the stress energy tensor in this theory. Good. And rho is just kind of like one component of the 0,0 component of this guy. So 2 points here. So that first Troutman condition is ensuring, in fact, that the Newton-Coriolis 2 form is closed. Prizes to which proposition in Malamute this is? 4.3.5. No? It is, right? Yeah.
Oh, yeah.
Must be a blast.
And at this point, I'm not assuming further curvature conditions. Sometimes you'll see this extra curvature condition appearing with the like upstairs, upstairs, downstairs, downstairs Riemann tensor curvature condition. You actually require that for Newton-Cartan theory to be kind of equivalent to standard non-relativistic gravity. I'll come back to that in a minute. So how does Newton-Cartan theory relate to standard non-relativistic gravity? So the way that philosophers of physics are most familiar with this is via Troutman geometrization and recovery. So if I've got my if I've got my Newton-Cartan derivative operator here, I can kind of split it up into some other flat derivative operator and then this gravitational potential, but split it up non-uniquely. So there's a kind of whole orbit of possibilities here associated with the Newton-Cartan connection. If I then assume that I'm dealing with an isolated subsystem, which means no cosmic expansion, which is exactly one of the things which is ruled out by this extra condition, then I can show that this new connection is also compatible with the metrics and recover the standard like non-geometrized Poisson equation. So I can recover non-relativistic normal Newtonian gravity when I impose that extra curvature condition as well. Really good. Okay, so just to flag super quickly that this is the way that philosophers of physics are most familiar with this, but our collaborator Quentin has got interesting papers about another way to understand the relationship between Newton-Cartan theory and ungeometrized Newtonian gravity, which he calls via the method of 3+1 projections. I'm not going to go into this more, but I want to flag it as something of philosophical interest. Okay, good. And then classical limit. There are many different ways in which you might take the classical limit of a relativistic space-time structure. So you might have a geometrical approach involving widening the light cones as c goes to infinity. And this can be rigorously understood using Euler's frame theory, which is kind of like a generalization of general relativity, which allows you to widen the light cones by having more models. You might do something a bit, on the face of it, stranger, which is known as null reduction, where it's actually kind of cool. If you take certain 5-dimensional solutions of general relativity, in particular what are known as Bargmann-Eisenhardt gravitational wave solutions, and you use the Julian-Nicolai ansatz, which basically amounts to like project all of what's going on there onto the null cones of that 5-dimensional geometry, then actually you get the structure of Newton-Cartan theory again. It's kind of all of that happens. Quite specific, but it's another thing that you could do to understand the relationship between relativistic and non-relativistic spacetimes. Or you could take kind of power expansion in 1 over c or 1 over c squared, which is, by the way, what we're going to do today. So to come back to Fletcher's paper, since he missed the first name drop. So Fletcher developed this kind of geometrical approach and says that it subsumes traditional methods, which are the third thing. And he also says that the way that he understands it is a way of kind of avoiding the charge that you're doing something strange in this first case by like changing a constant of nature. I think that all of that is valuable and great, but I'm doing a different project and I'm just going to do traditional methods. Cool. So to give you an idea of what's going on with these traditional methods, like a lot of people have looked at this, here's how Kunzel described what's going on in the 70s. I've got some parameter lambda and I just expand my metric in that parameter. So I could expand my inverse metric here, and then the first term would be this h thing, and then I get higher order powers in lambda. If I expand my downstairs metric, I'll get some one forms here, tau tau, and then some extra terms as well. Then if I impose things like, I know that these guys give the delta function, right? Because they're the inverses of each other. If they then plug those expansions in there, I'll start getting stuff out like tau being orthogonal to h, and further conditions for like the higher order terms in the expansion of the metric and so on. So this is the way that, very roughly speaking, these non-relativistic power expansion type approaches to the non-relativistic limit work. Okay, good. So that was the first bit on background. Is everyone be happy? Good. Okay, so now we'll go on to constructing the non-relativistic trinity. So what was known at the start of 2013? Well, we knew that there was a relativistic geometric trinity relating general relativity and its teleparallel equivalent and the symmetric theory. And people were getting more and more attuned to the fact that the non-relativistic limit in one way or another of the relationship between general relativity and teleparallel gravity was the relationship between Newton-Cartan theory and its teleparallel equivalent. So, for example, Nick Tay and I asked in a 2018 paper, is Troutman geometrization equivalent to teleparallelization? And we gave there an affirmative answer and tried to demonstrate this by null reducing this pair down here. I actually think I would nuance my answer to this question now, so maybe we'll come back to it. Maybe the more natural thing to do would have been to take a 1 over c expansion rather than null reduce, and that was done in a very nice paper by Philip Schwartz that came out last year. So he did a 1 over c expansion of the teleparallel equivalent of general relativity, and just got this teleparallel equivalent of Newton-Cartan theory, which I'm going to describe to you today. But some stuff has not been done yet. So no one had taken the non-relativistic limit of the symmetric theory, and the completed non-relativistic trinity had not been constructed. Okay, a bit more differential geometry. Right, it's all good. Previously I've run under, so I was like, I'm going to pack this with as many slides as possible. So I'm definitely going to run under, but now I'm thinking that I might in fact run over. But so recall again that the formula for the connection components of a symmetric and torsion-free Galilean connection is this thing, where I've got these b's, little b's and big b's, so this is not fixed uniquely absent further choices about like what big B is, for example. The story is going to get more complicated if I do a non-relativistic connection with torsion or non-metricity as well. So if I'm taking the difference tensor between that connection which I had on the previous slide and some non-relativistic connection with torsion and non-metricity, and I would get this, in fact, where I've got some non-metricity terms over here, and I've got some torsion terms over here. So you just get more stuff, as you would expect, if you're doing using a non-relativistic connection with torsion and non-metricity as well. From that formula, you can then just set the non-metricity to 0 and see what the reasonable expression for a non-relativistic contortion tensor would be, and it's this thing. And you can also, you don't really need to worry about what's in the expressions, but we can go there. And you can also do the same thing with non-metricity. So take that general expression for the difference tensor, but then just set the torsions to 0, and then I'm going to have a plausible expression for the non-relativistic distortion tensor, which is this L hat over here, and that has this expression. Just as a side note, in the relativistic case, we could kind of take this difference tensor and see it as the sum of the contortion and relativistic contortion and relativistic distortion. It's not so easy to do that here because, in fact, these things are related to each other. So just as an illustration of this, you can derive this expression, which says that this torsion tensor is related to this part of the non-metricity of the clock form. So they're kind of related to each other. So you can't just so easily like tease out like what's torsion and what's non-metricity. You kind of have to like set all non-metricity to 0, and then you get your reasonable expression for the contortion tensor, or set all of the torsion to 0 and then get your reasonable expression for the distortion tensor. That won't really matter, it's just on the side. Okay, so now let's construct the trinity. So, if the Galilean connection derives from the non-relativistic limit of a Lorentzian connection, it's been known for a while that it takes this form, which is a special case of the generic form with the generic Newton-Coriolis 2 form that we had before. But what you get as like the 0th order term in your expansion of the connection is this thing where this guy is an exact Coriolis field already. Cool. So bear that in mind and we'll come back to it. So now we want to take the non-relativistic limit of the contortion tensor and the distortion tensor using a 1 over c or 1 over c squared expansion. If I do an expansion in 1 over c squared for the contortion tensor, I'll end up getting this expression. We could go through this in more detail if people want. There are a few different ways in which you can approach this. So this is kind of done in most detail by Schwarz because he was the person that actually his whole paper is about taking the non-relativistic limit of teleparallel gravity. The way he approaches it is he thinks about the Cartan equation for the torsion tensor dE plus omega wedge E, and then he uses series expansions for the tetrads and for the spin connections to get his series expansion for the torsion, and then he plugs that in to get his series expansion for the distortion tensor. Sorry, for the contortion tensor. With the non-metricity, you could just series expansion the metric and use that as a way of getting your relativistic non-metricity tensor. The maths is somewhat tedious, but let me skip to the result. Just before doing that, though, the general prescription is going to be kind of the obvious thing of write down the Einstein equation for general relativity in terms of its teleparallel or symmetric teleparallel contortion or distortion like we did before, and then take the non-relativistic limit of those guys using these expansions. Yeah.
Sorry, you said before that you would vary the action for both the metric and the other tensor. Then you get more equations. Mm-hmm. You don't get just the Einstein equation. So why is the equations of motion just equivalent to replacing in the Einstein tensor the terms with the contortion?
What other equations do you get?
Well, you have the equations that you get from the variation of the other term.
Flatness. Rigidity.
Mm-hmm.
So you get compatibility, Martini.
Right. So I think that's not necessarily a problem for me, right? I just write the action using the other variables, and then when I vary, I'll get different equations, which will be like not flatness, or one of the other things will vanish.
No, wait, the Palatini, you vary the tetrad, right? And the connection.
Or you could vary the metric.
Okay, but in any case, in these cases, you said you vary the metric for these other actions, the metric and the other tensor, the contour, I don't remember. So you get more equations of motion.
Mm-hmm.
And you're saying that these equations of motion jointly, they are equal to the Einstein equations written in terms of the contortion and distortion?
That's what I'm saying, and that's what the physicists who work on this say as well. So this has gone through in, for example, the Heisenberg review paper that I mentioned. But just to be clear, everything that we're doing is using the equations of motion from this point onwards.
We don't have actions for...
That's actually going to be kind of important. So actions for non-relativistic gravity are a tricky business. Easier to work with equations of motion.
I mean, you can, like, if you think when you do your Lagrangian variation, you put weights on various components of the connection, so they're going to vanish.
Cool. We can talk about it more.
Yeah.
All right, so take the non-relativistic limit of general relativity. This is like old stuff. Get the geometrized Poisson equation, variant divergence of the stress energy tensor vanishing, and you'll get this expression for the connection coefficients where I've got this exact Coriolis field. If I do the same thing for the parallel case, I'll get something like this, like even more nasty looking than the original one. Where my contortion tensor, which is featuring in this equation of motion, is this long expression here, but the Riemann tensor vanishes and we have compatibility with the two different metrics. And then in the flat, non-metric, torsionless case, I've got something which is similar. I've got this long equation of motion here, where this is the non-metricity which I get from the limit, and where I've got vanishing curvature and vanishing torsion. Just as an aside, it's kind of important. Like, there's not just one non-metricity when you go to the non-relativistic limit of a relativistically non-metric theory, because I've got the non-metricity of H and the non-metricity of T, and also, although they turn out to be related to each other in various ways, the non-metricity of the downstairs object and the non-metricity, I guess, of this vector field B, which was featuring in the connection. We have conjectures about like being able to get rid of these guys, but I want to flag like a bit complicated here. So in each of these cases, the Coriolis field is exact, implying that it's closed, implying that you get the first homogeneous Troutman condition for free in the limit, which is also known, but you don't get the other one in the limit. Setting the first equation in each case, since the first equations in each case are equivalent, considering the definition of this derivative operator with the formula for K or for L, and correspond to the geometrized Poisson equation, each of these systems of equations are equivalent and lead to the classical Newtonian theory when, in addition, you impose this curvature condition. Wouldn't lead to any of these guys being equivalent to the non-relativistic flat space-time potential-based version of Newtonian gravity if you didn't impose this curvature condition or its torsion-full or non-metric conditions. You have to actually impose those as well. Okay, so how does this relate to non-relativistic gravity? Well, I was already telling you something, sorry, as in how does this relate to like classical flat space-time Newtonian gravity? I was already telling you something about this. Just to go back to Quentin's paper, so with his 3+1 projections, he can show that you can obtain standard potential-based Newtonian gravity via his method of a 3+1 projection of Newton-Cartan theory. But to get like the standard theory, he has to impose this condition as well, so it kind of all fits together. This flat space-time potential-based version actually can also be understood as the non-relativistic limit of 3+1 GR, which is something that Quentin does properly and Niels and I do heuristically. So that's also interesting, I think. And yeah, I've already said it, but for the teleparallel equivalent of Newton-Cartan theory, or the symmetric teleparallel equivalent of Newton-Cartan theory, you can recover potential-based Newtonian gravity once you impose the torsion, full, or non-metric equivalence of this expression. The picture then ends up being something like this, which I think is like helpful. So we've got our relativistic geometric trinity here. I can do my non-relativistic limit to get my non-relativistic geometric trinity, where these guys are related by 1/c expansions. If I impose that second homogeneous Troutman condition, I'll get to normal potential-based flat space-time Newtonian gravity. This is, just read this as like ng. And that's going to be related via a projection of the 3+1 GR as in. So I think this is a nice kind of complete picture about what's going on. And it maybe this is the sense in which I would revise what Nick and I said. So Nick and I were saying that I think the right way to understand the relation. Okay, so teleparallelization is basically relating these two things, right? You're trading torsion for curvature. And it's not exactly like that's what's going on down here with geometrization and recovery. Rather, geometrization and recovery are like links between the nodes of this trinity and normal flat space-time potential-based Newtonian gravity. So I might like revise what I said with Nick, but I think this like makes clear what's going on. Yeah.
So just a quick, because it might have been just a bit quick for me. So the 3+1 projection on the GR side,
Yeah.
is that like doing a sort of just a sort of Hamiltonian?
Yeah.
Okay.
Yeah.
So then presumably that only recovers a sector of that.
Sure. Okay, to mention one other thing, which is kind of interesting, I think. We've been talking about so far a general version of non-metricity, but you might look at a special case of non-metricity, which is where the non-metricity decomposes into like a metric part and then what's known as a non-metricity one form. So this is just like a special version of non-metricity. But it's the one that Weil was interested in the 1920s, because Weil thought that by introducing non-metricity like that, he could identify the electromagnetic four-vector potential with this one form and unify gravity and electromagnetism. It turned out not to work because Einstein complained that the theory predicted the second clock effect, which is not observed, and so people abandoned that approach. Although, interestingly, as an aside, a couple of physicists from Cambridge recently have been arguing that there's a way of doing Weil gravity which would not have a second clock effect. So Hobson and Lazenby have a couple of papers in PRD from a couple of years ago. So I think that's also something which merits a bit more philosophical scrutiny. Okay, so historically, yeah, he generalized the Riemannian geometry by going to this version of non-metricity. This is still a somewhat active field of research, so Will and I have been kind of rooting through like papers on Weil gravity recently, and actually there's a kind of uptick recently, which is interesting. And they have this Weil gauge symmetry, if you care. So for Weil geometries, the distortion looks like this. Yeah, I could do a 1/c expansion of my Weil geometry. It's just like all a special case of what we were doing already. You get these non-metricities, and you get this expression for my Weilian non-relativistic distortion tensor. And you can also get an expression for your non-metric Weilian theory written mostly in terms of the non-metricity one form. Even cooler though is this, like everyone's favorite paper. Ehlers and Pirani Shields 1972 shows that if you are given a piece of projective structure and a piece of relativistic conformal structure, which is like for them a set of cones at every point, kind of light cone structure that you would expect, then look, here's some equivalent ways of characterizing it. I can think about an equivalence class of metrics which disagree on scale, or I can think about a field of infinitesimal null clones over M. For projective structure, you can have projective structure will be picked out by the equivalence class of connections which differ by these terms, but these connections agree on geodesics but might disagree on parameterization. So that's what projective structure is. What EPS showed, amongst many other things, is that if I give you a piece of conformal structure and a piece of projective structure, then that will actually fix for you a Weil geometry of the form that we were looking at before with that relativistically Weilian non-metricity distortion tensor. So you might ask, can I do something similar in the non-relativistic case? Well, we would first need a notion of non-relativistic conformal structure, and that seems to have been something which has puzzled people for a bit. So there's a paper from the late 80s by Ewan and Schmidt who say one thing which on reflection seems kind of wrong. And there's a paper by Eric Curiel about a non-relativistic version of Weil type theorems, which is followed up in another Eleanor March paper from recently about non-relativistic twistor theory, where she kind of rewrites and slightly generalizes what Curiel says to this, which I think is a good definition of non-relativistic conformal structure. So let M be a differentiable manifold. A non-relativistic conformal structure is an integrable rank 3 distribution on M which leaves S an equivalence class of conformally equivalent spatial metrics on M such that there exists a one form T on M orthogonal to all of the H's such that for all points and all S and all tangent vectors sigma to S at P, these guys kill each other.
What's the intuition behind that?
could be better put like this. You have facts about angles on every leaf of the foliation, and those facts about angles smoothly vary from between the leaves. And that makes sense, right? Because conformal structures are like facts about angles. So in the spirit of EPS, you can now ask, what would happen if I tried to glue together or combine my non-relativistic conformal structure to find like that with projective structure? And I was playing around with this under extreme time pressure to finish a book. But it was cool that once you do this, you actually find the kinds of non-relativistic Weylian spacetime theories which I was just talking about. And it's actually quite cool that you can compute the non-relativistic distortion tensor, and it's the same thing pretty much that Will and Quentin and I wrote down in our paper, which wasn't directly anything to do with EPS. So you kind of get the same thing from two different angles. You can glue together these non-relativistic conformal structures and projective structures to get that non-relativistic Weyl theory, or you can get that non-relativistic Weyl theory by taking a non-relativistic limit of a relativistic Weyl geometry. Neat, right? Everyone should buy this book. Okay. So there's the Trinity, and there are some non-relativistic Trinity, and there are some interesting observations about it. Now let's think about common structures to the relativistic Trinity versus the non-relativistic Trinity. So let's start off with some philosophical remarks. So far we've taken the non-relativistic limit of the relativistic geometric trinity to construct a non-relativistic trinity. Given the dynamical equivalence of the theories, there might be a worry about underdetermination of theory by evidence for both trinities, because it looks like these theories make the same predictions in some sense, and yet they make different claims about the geometry of the world. So we need to say at least something about how to avoid that specter of underdetermination. The way that Ellen and Knox does it in her 2011 paper is to invoke space-time functionalism is what I would have said like 6 months ago, but I'm no longer sure, because you actually said that her paper should be understood as an argument for space-time functionalism, which I need to think about more. But ultimately, one of the things that she's saying in that paper is there's no like good way of interpreting teleparallel gravity, the teleparallel equivalent of general relativity, on its own terms, and its ontology is really that of general relativity, and so there's really no underdetermination there. You might or might not like that. I'm not entirely sure I'm on board with these papers. But another way in which you might go in trying to banish the specters of underdetermination here is just to identify like what the common mathematical structure is and whether I can interpret that by itself. So this is kind of conceptually in the same spirit as, you know, you have this worry about Leibniz shifts for Newtonian mechanics set in Newtonian gravity, and then you realize that the common structure is Galilean space-time, so why not believe in that instead? So it seemed worthwhile to try and identify like what the common structures to the two trinities are. So as I've presented the relativistic trinity, all three nodes are committed to a metric. They just disagree about what the connection is. That's not always the case in how people present these things. So especially like slightly older teleparallel gravity literature, they don't really use metrics that much. They use tetrads all the time. But you can still build a metric using those tetrads. And so it's still there. It's still, in Eleanor Knox's terminology, waiting in the wings. It's then the case that from that metric, you could define a Levi-Civita connection. It's implicitly definable given the metric, because once I give you a metric I've given you, its unique, compatible, associated connection. See Barrett paper, but also Max Frank Klasky paper from 100 years ago. What's that?
Sorry, isn't it explicitly?
Yes.
Yeah, sorry. Definable.
It implies that it's implicitly defined, so it's not false.
Not in the Tarski-Grotowski sense. In this sense, it's implicitly definable.
In the spirit of hammering through the slides, can I? So once you've got that, you could write down the Einstein equations, right? I've already got my like teleparallel version of the Einstein equation, so it seems like I've got all of the resources to write down just the Einstein equations featuring the Levi-Civita connection in all three of these theories. And so it seems like there's a good case to be made that the common core of the relativistic trinity just is general relativity. That's an argument. It's not the line that we took in our original version of the paper, it's the line that I would take now. And I think that came out of nice discussions between Will and Oliver and Adam a few months ago, so all good. Okay, but what about the non-relativistic trinity? So we need to introduce one more piece of machinery, which is a standard of rotation. So remember that a connection is giving you a standard of non-rotational acceleration and a standard of rotation. And people often say post-Saunders that in light of Newton's corollary 6, maybe all we need in Newtonian gravity is a standard of rotation and not a standard of non-rotational acceleration. So let's try and build a theory which just has that. So a Maxwellian spacetime is in that sense weaker than a Galilean spacetime, and it just has this standard of rotation. But it's not able to tell you whether one set of trajectories is accelerating and another's not, because you don't have that structure. Sorry, non-rotationally accelerating and another's not, because you don't have that structure. You just have the standard of rotation. So if T and H are compatible temporal and spatial metrics on M, then the standard of rotation compatible with these guys is a map from smooth vectors on M to rank 2 tensor fields such that all of these nice conditions are satisfied, and that seems to do the job that we want from a standard of rotation. So that was written down first by Weatherall in a paper from 2018. Cool. So you might ask, under what circumstances does a non-metric or torsionful non-relativistic spacetime admit of a standard of rotation compatible with these two things? And we have 3 propositions here, and I should be totally clear that all 3 of these propositions in their formulation and proof are due to Eleanor. So props to her, as it were. So here's the first proposition. Let M, T, H now be a non-relativistic spacetime where T and H are compatible and where we've also got these non-metricities, so they're not metric connections. This is not a metric connection. Then this map is a standard of rotation compatible with tau and H, just in case this condition on the non-metricities is satisfied. Likewise, for the torsionful case, if I've got this torsionful non-relativistic geometry, then I've got a standard of rotation compatible with tau and H, just in case the torsion tensor with all of the indices upstairs vanishes. And there's also a common standard of rotation for the non-relativistic trinity in the following sense. So consider this triple M tau H with tau and H defined as before. Then consider 3 connections: a curvature-based connection, a non-metricity-based connection with these non-metricity tensors, and a torsion-based connection. And then consider the curvature-based connection be related to these guys by the non-relativistic distortion and contortion tensors. Then these are standards of rotation compatible with the metrics, and they equal each other just in case these conditions are satisfied. So you can impose some conditions on your non-relativistic non-metric theory or your non-relativistic torsionful theory, and they will agree on what the standard of rotation is. Cool. Now, in the symmetric teleparallel equivalent in Newton-Cartan theory and in the teleparallel equivalent, the 2 curvature conditions actually ensure that that is the case. I get these things from the R upstairs, upstairs, downstairs, downstairs is equal to 0 curvature condition for Newton-Cartan. And I get this thing from the R ABCD is equal to RCD AB condition. So if I'm imposing the curvature conditions which I have in Newton-Cartan theory, then when I think about their equivalence in the symmetric teleparallel equivalent in Newton-Cartan theory or the teleparallel equivalent, I'll have the satisfaction of these conditions, which is sufficient to ensure that there's a common standard of rotation between the nodes of the non-relativistic trinity. So the result is that each model of Newton-Cartan, understood as now having both of these curvature conditions and its associated models of the symmetric teleparallel or teleparallel theory, account a unique Maxwellian spacetime. This second curvature condition also guarantees that this Maxwellian spacetime is unique in the entire space of models. So these 3 theories can all be understood as theories set on the same Maxwellian spacetime. And that's expected because all 3 nodes of the geometric trinity with those curvature conditions imposed are supposed to be equivalent to standard flat spacetime potential-based Newtonian gravity. Any theory which is empirically equivalent to that theory must also distinguish the same class of frames, which requires agreement on the Maxwellian spacetime structure. So you can show that with those conditions imposed, you have a common standard of rotation, but you might also ask, like, can I actually write down dynamics using that standard of rotation? But you can, thanks to Elliot Chen, who was, I believe, one of Jim Weatherall's DPhil students, and also Eleanor at almost exactly the same time. So this is a theory which you might call Maxwell gravitation, and has these models, and you can write down dynamical equations for it, and plausibly that is the common structure for the non-relativistic trinity. So that would substantiate the claim that MG, Maxwell gravitation, is the dynamical common core of your non-relativistic geometric trinity, and paves the way for an interpretation of Newtonian gravity on which it has strictly less structure than that of a connection. So in other words, just focusing on like the downstairs bit of the diagrams that we were drawing before, you've kind of got Maxwellian gravity living in the middle. Good. So what else can we do with this? I'm just going to mention two things, but I'm sure there are many, many others as well. So if you're not sick of trinities yet, then fear not, because there are more such things to construct. So I think one thing which I think philosophers should look at more is chiral gravity, which is the ultra-relativistic limit of a relativistic theory, where you narrow the light cones, you maximally narrow the light cones, so everything is going like super fast. Well, maybe that's not the right thing to say. So you attain the space-time by narrowing the light cones or doing a c-squared expansion rather than a 1/c² expansion. So to my knowledge, discussion of this goes back to Lévy-Leblond, but Datacourt in the 90s had like the first full paper about doing the ultra-relativistic limit of general relativity, doing these kinds of expansions. And he says things which I think is just like interesting about these spacetimes. So note that in a chiral spacetime, there are no interactions between spatially separated events, and no true motion occurs in the limit except for tachyonic motion. However, the isolated and immobile physical objects show evolution. So it's kind of like a weird thing that's going on in this spacetime. It'd be nice to think more about like the metaphysics of chiral gravity. How would I take a ultra-relativistic limit of a relativistic spacetime theory? This is, like I say, in Datacourt, but I think explored more systematically in Hansen's PhD thesis from 3 years ago. So he writes the metric and its inverse in what people in this tradition call pre-non-relativistic variables, which look like this. So you kind of like split it up into like the spatial bits and the temporal bits. And then they do expansions of those pre-non-relativistic variables. Hansen does this in this way for general relativity. I don't really see any big conceptual roadblock to being able to do this for the other two nodes of the geometric trinity if you really wanted to. And already happened this year, right? You could also do a type 2 limit, which is interesting. So clearly, if you take the non-relativistic limit of a Lévy-Civita connection of general relativity, you don't get torsion. But what you can do, and what Hansen and Hartong and Obers and others who work on non-relativistic gravity have been doing recently, is to define a slightly more general relativistic connection using these pre-non-relativistic variables, and then to take the non-relativistic limit of that. And you get a different kind of non-relativistic space-time theory with both torsion and curvature, which they call type 2 Newton-Cartan theory. That, I think, is of both physical and philosophical interest for at least the following reasons. It has an action, unlike normal Newtonian gravity, so, like Newton-Cartan theory. And once you've got an action, you can start doing more sophisticated things with notions of energy and so on. So it seems like a nice thing to have for a non-relativistic space-time theory. And curiously, this theory, they also argue, answers many of the tests of general relativity, or many more than Newton-Cartan theory does, which I think is kind of interesting. In fact, they think that the only thing that distinguishes this version of Newton-Cartan theory from general relativity is a gravitational wave-type experiment. So their argument is that pre-LIGO, actually, we could have argued that the universe was still non-relativistic, which is interesting. And Will and Marco Sanchioni and I talk about that a bit in a draft. So why not take the type 2 limit of geometric trinity of gravity? One reason is that it's like mathematically nightmarish, but it'd still be nice to do. Cool, so let me summarize. We've constructed a non-relativistic geometric trinity of gravity and argued there's a common core is Maxwell gravitation. Unlike the common core of the relativistic trinity, which is general relativity. And we have tied together thereby some of the debates in the philosophy of space and time literature, because we've seen how Maxwell gravity fits in with the relativistic trinity, fits in with the non-relativistic, so on. And we've seen some future questions for further pursuit. So, thanks.
Thanks, James. That was probably